Okay, in this video, we're going to look at the residue theorem. We are going to just introduce this theorem and the formula that it states, and we're going to do a sketch of a proof of the theorem, and then in the next video, we're going to look at how to use it to evaluate integrals. All right, so so far in our study, we have encountered this theorem, which is Cauchy's theorem, which says that the integral of f of z around a simple closed contour, whereby f is analytic everywhere inside and on the contour, this is going to be equal to 0. So that is Cauchy's theorem. Then we have also seen the case where you've got a simple closed contour and f is analytic everywhere here, but this integrand is going to be singular at z0. So then Cauchy's integral formula states that this integral is going to be given by that. So that is Cauchy's integral formula. So it caters for the case where you have got a simple closed contour and your integrand is singular at just one point. And then in our video on the residues, we showed that if f is analytic everywhere, but singular at z0, if you expand f in a Lorentz series and integrate on both sides around c, then this is going to be 2 pi I times a -1, where -1 is the residue of f of z at z0. Okay, so what this means is that in the theorems or results that we have so far, we can evaluate integrals with a maximum of one singularity inside our contour. So either one singularity or no singularity at all in the case of this first one. Now, the residue theorem is going to enable us to evaluate integrals with more than one singularity inside our contour. So what has happened so far is that in order to use this one, if we've got like two singularities, we've had to like use maybe resolve into partial fractions or something like that. So the residue theorem is going to enable us to do that without using partial fractions or something like that. So the theorem goes as follows: if f of z is analytic inside and on a simple closed contour C, except at a finite number of singularities, which denote z0 to zk. So this is our simple closed contour and these are our singularities. Then the theorem states that the integral of f of z around C is going to be 2 pi I times the sum of the residues of f of z at each of the singularities inside. So we're summing here from residue at z0 to residue at zk. Of course, we can write this in summation form like that. What we're going to do, we're just going to sketch a proof of the theorem for the case where we've got only two singularities. So then extending it to the case where there are 3, 4, 5 is pretty straightforward. So what we're going to do is we have got this contour, so let's call it C. Of course, the positive orientation of a contour is always considered to be the direction which is counterclockwise, or if you're traversing on the contour, then the inside of the region must always be on your left. What we're going to do is we are going to introduce a modified contour. So let's have a go at this. If we introduce a modified contour, so along these points, it's going to trace exactly the same contour as C, then we go inside and we circle one of the residues, so it's coming in this way and out that way, and then again we're tracing basically the same as C, so same as C, and then when we get to this point again we go in, we circle Z0, and then right round to where we started. Now so in here, around here, and around here. Now if you look at this purple contour now, if I can okay, maybe before I do the shading, so let's label this part C1 and this one C2, C3 here. This is going to be just negative of C2, because actually we're going to imagine that these two are so close to each other, they are literally, you know, so one is the same going one way and the other is the same going the other way, so they're going to be very close to each other, so that this is literally a closed contour there around Z1, the same there. So that's going to be minus C2, so this is going to be C4, C5, C6 here, and so going out is minus C5, and then of course this already we have said is C1. So now this purple contour is such that if we shade everything, that it's still a simple closed contour, but you're going to notice that it actually closes the singularities out. So the singularities are actually outside this modified or deformed contour. So you can see that Z0 and Z1 are now outside. So let's call this contour C bar. So C bar is C1 plus C2 plus C3 minus C2 here, and then plus C4 plus C5 plus C6 minus C5 here out, and then that covers the whole thing, because this bit here is C1. Now since C2 cancels itself out, then we can just simply cancel this out. The same thing with C5. So C5 here cancels out. So that means C bar is literally C1 plus C3 plus C4 plus C6. Notice that C here, the original contour, in terms of the pink contour, is just C1 plus C4. Okay, So here, if we regroup this C1 plus C4, that's just C that we had before we introduced the deformation. The other thing to note is that the contours C3 and C6 are in the negative orientation because they are clockwise. Okay, but what we're going to do here is we're going to say, well, since now the singularities are outside this modified contour, then the integral of f around C bar must be equal to 0 according to Cauchy's integral theorem. So that means the integral of f around C1 plus C4, C3 plus C6, f of z is equal to 0. Now we just said C1 plus C4 is C, so we can rewrite this integral of C plus C3 plus C6 of f of z equal to 0. Again, we can write this as integral of f of z, and then remember, because these two are negatively oriented, so that's going to be f of z around C3, but negative f of z around C6, negative, and this is equal to 0. Now C3 and C6 are close contours around singularities Z1 and Z0 respectively. Now, according to this result here, if you evaluate a function around a close contour and it's singular at Z0, then this is going to give you 2 pi I times the residue at that singularity. So that means here, this is going to be the integral of f of z minus 2 pi I C3, residue inside C3 is Z1. So that's going to be the residue at Z1. Residue at Z1 of f of z. But similarly, this one is just going to be 2 pi I times the residue of f of z at Z0. This is equal to 0. If you now bring this term across to the right-hand side, we now have the result of the residue theorem, that the integral of f around C is going to be 2 pi I times the sum of the residues of the of f of z at the singularities inside C, which is basically what this residue theorem is stating. So basically that's how the theorem is derived. It's a sketchy proof, but it is adequate. So yeah, we're going to take it up to this point in the next video. Then we're going to start using this result to evaluate some integrals. Thank you.